current session, Bulat has just arrived and he's in Ag and Resource Economics, and then the next speaker, Takuya, is here in Economics for his second year. So, without any further ado, let's start.
Thank you for the introduction. I would like to present a joint work with Jose Montiel from Columbia University and Matthias Meyer today. This will be an econometric theory talk, but to make it more interesting to listen, I will talk more about the application of that method that we developed. So the title of the talk is Effects of the Unconventional Monetary Policy Estimated Within a Structural VER Model with Set Identification. And it's based on a paper called Delta Method Inference for a class of structural VERs, set identified structural VER models. So structural VER models they became a standard model in empirical macroeconomics, but not only macroeconomics, but also in many other areas like analysis of commodity markets, to name a few. And the model takes a very simple form. It's a linear regression model that relates a vector of observed time series. In my case, it will be gross domestic product, inflation index, and interest rate. And it relates current value of this time series vector with the previous values. And this model can be easily estimated using standard OLS method. However, so what makes this method particularly appealing is that you can do a contrafactual analysis. You can study what will happen to time series DGP, or gross domestic product, in response to a monetary policy announcement or monetary policy shock or some other kind of shocks. And the goal of analysis, the reason why people use those structural VERs is to study those responses, like how inflation or gross domestic product will react to a certain shock, like monetary shock, over time. So here, those structural shocks, they are denoted epsilon here, and they are multiplied in general by some matrix B. So the problem, the econometric problem while analyzing these models is how to recover that matrix B using estimates. And unfortunately, using just OLS estimates, one cannot recover that matrix B uniquely. Instead, we can only recover the covariance matrix, which is the square of that matrix B. So in order to perform a contrafactual analysis, we need to impose some additional theoretical restrictions to recover that matrix B. In case if we can recover it uniquely, we say that the structural VER is point identified. In case if we cannot recover it uniquely, we can still probably provide some bounds. And in that case, I say that the structural VER is set identified. And in this paper, I will study structural VERs set identified by restrictions on a single structural shock, such as a monetary policy shock, without imposing any prior distribution assumptions on the matrix B, as is common in the current literature. So to illustrate our approach,
Do you want to just give what the simplest identifying assumption would be on B?
Yeah, the simplest identifying assumption would be that gross domestic product and inflation, they do not react to unexpected changes in monetary policy in the same period, but they can react over time. So this is a standard assumption used in the when this literature just started, and that assumption is sufficient to to point to uniquely identified columns of that matrix B. So to illustrate our approach, I will show how to use our new method that we developed to impose bounds on possible effects of quantitative easing policy announcement that took place in 2010. So this paper provides a new algorithm that allows one to compute bounds for the maximum and the smallest possible values that a structural impulse response function can take, subject to given theoretical assumptions. Now I will talk more about what kind of assumptions we can deal with on the following slides. We provide conditions under which those bounds they are directionally differentiable functions of OLS coefficients, and based on that result, on directional differentiability result, we provide analytical confidence sets for impulse response functions, and our confidence set have attractive computational properties, and also they have very good Monte Carlo properties in finite samples, and they outperform existing methods in terms of length. So let's get back to the model. A structural VER model is given by this vector linear regression. So I'll call those matrices A and the squared matrix of matrix B, which is covariance matrix of the shocks in the estimated regression. I'll call those two parameters reduced form parameters, and I'll put label mu on them. That set of parameters is uniquely identified using data, and we can estimate it using ordinary least squares. However, in order to perform counterfactual analysis, we need to construct a square root of that matrix sigma, and that square root, which is matrix B, is not uniquely identified. Still, suppose that we know that matrix B, then the object of interest would be how time series with index I, say GDP, reacts to shock number J, say monetary shock, monetary policy shock, K periods after that shock. And this object can be represented as a certain function that is nonlinear in the parameters that we can estimate, and it's linear in parameters that we cannot estimate.
Yes, clarification. So the idea is the shock does not contaminate your estimation of A. So it's just a question of getting the structural response. So the sort of shock you're interested in, you can still consistently estimate A and sigma.
Yeah, without imposing any assumption about the shock, I still can consistently estimate A and sigma. Of course, there are certain regularity assumptions like existence of moments, but without any assumptions, without imposing interpretation for epsilon, we can estimate mu. So now suppose that we have some additional theoretical assumptions like monetary policy shock does not affect GDP in the first period. And those kind of assumptions, they can be represented as linear functions in column, as certain equalities or inequalities that are linear in that matrix B, in the columns of matrix B, and maybe nonlinear in mu. And then once we impose those extra theoretical assumptions, we can explicitly write down the largest and the smallest values that structural impulse response function can take subject to those assumptions in terms of a mathematical program. This is a nonlinear program. I will show you how to compute values of that program efficiently and how to perform inference on those upper and lower values that impulse response function can take. In this paper, I only study assumptions that restrict a single column of matrix B. It is sufficient to study structural responses to one particular shock, say monetary policy shock. If you would like to study impose restrictions on monetary policy shock and say fiscal policy shock at the same time, then that would fall outside of our framework and we cannot deal with at the moment. So within this framework, we can always formulate the problem this way. So there are a number of theoretical restrictions that were proposed in the literature. So I'll go through them quickly. They come from certain economic assumptions, and the first type of restriction we can deal with is restrictions on impulse response functions, and the motivation in form of inequalities and the interpretation for those restrictions can be the following. Suppose that we are not sure if monetary policy shock does not affect inflation in the first period, but we know that from the economic theory that contractionary monetary policy can only reduce prices, it cannot increase prices. So we can impose restrictions in form of signs on impulse response functions and to identify monetary policy shock. So this is the first type of restrictions we can deal with. Also, a number of other restrictions were proposed in the literature, like restrictions on the long-run effect of, say, technological shock, considered in that one-charge wash. We can deal with that within our framework, or restrictions on contemporaneous so-called short-run restrictions on contemporaneous relations between variables. You can think about it as we suppose that we have some of the equations in the structural VER represent the monetary policy rule. Then from economic theory, we know what should be the signs of the coefficients in the monetary policy rule. And finally, Killian and Murphy imposed restrictions on the elasticity of demand and supply shocks to study oil markets. And these kind of restrictions, they are also linear in columns of Bj and can be also studied within our framework. So these are restrictions we can deal with. All of them are differentiable in parameters mu. And so the first result that we provide an algorithm how to compute largest and the smallest value of the program. So mathematical program that I showed you earlier has both equality and inequality conditions. If that program would only have moment equality conditions, it's possible to write down explicit formula for the maximum and the smallest value of that program, and we'll call that formula V bar Kij subject to a set of restrictions. Then our algorithm is the following: we can replace inequality restrictions by the corresponding equality restrictions, and consider all possible combinations of active moment or active inequality restrictions. And for every active combination, for every active set of restrictions R, we can characterize the value of the program explicitly by a certain formula that's given in the paper, and we only need to check if that point at which that value is attained, if it's feasible in the full program, in the original program. If it's feasible, then we write it down somewhere. If it's not feasible, then we drop it. And So in order to compute the value of the original program, we just need to consider all combinations of active equalities or active inequalities, and then just take the maximum over feasible solutions. So, and in this setup, number of the points that we have to consider is finite, and it's very fast to compute in practice, and it provides numerically correct value functions, even in this setup where, in general, so I would like to remind you that structural VERs result in mathematical programs that are nonlinear and non-convex in general. So we can characterize global optima using this finite number of steps.
So if you had a VAR with 3 variables, is that going to be computationally difficult as well? I mean, what?
No, it's not. It's
so why are we having so much? Is it the number of elements of the VAR?
Is it computationally difficult for existing methods?
Existing methods?
Yes, it is, because they would have to construct set of grid points. Right, maybe in 3-dimensional cases this is not such a big deal, but in 3- and 4-dimensional cases, the existing methods have substantial numerical errors.
So the grid is over what?
Grid over Bj.
Okay. Right.
Grid over columns of the orthogonal matrix. Oh, sorry, of the matrix B. So second result, we provide conditions under which those larger and the smallest values of impulse response functions, they are directionally differentiable in mu. And I don't want to talk about it for very long. There is a closed form formula in the paper, and we use that result to construct analytic delta method type confidence set, under assumption that we have an estimator of the reduced form coefficient that has asymptotic normal distribution. And that is definitely the case when you have a stationary time series with finite moments. So under asymptotic normality, we provide this confidence set for entire set of values that structural impulse response function can take. And to construct the set, we need to compute the lowest possible value using our algorithm, the largest possible value, and then subtract standard errors based on the derivatives that we provide, multiplied by by the quantiles of the normal distribution. So this is a very familiar form. I would like to stress that big advantage of this approach is the computational speed. It's very fast to compute. Standard errors has closed form formula, and so brief comparison with existing methods. So there are two approaches, two broad approaches to this problem of inference in structural VRs with set identification. First approach is to impose certain prior distributions over matrix B, which is not identified. So matrix, that structural matrix B is not identified, but we can impose certain probability distribution based on some extra assumptions. So once we do that, we can perform standard Bayesian inference. So the drawback of this approach is selection of the prior over that matrix B is somehow arbitrary in many applications, and it's well known that in set identified models where parameters are not uniquely identified, those credible sets, they will not cover the full set of possible values that structural impulse response function can take, even if you have very large samples. So those Bayesian approaches, they will always miss extreme points in the some extreme values that impulse response functions can take. In our trend of literature studies non-Bayesian approaches, and there are two papers. One is based on robust Bayesian analysis, and the other one is based on moment inequality approach. They don't suffer from that problem. They don't suffer from the arbitrariness of the bias Bayesian prior. However, both of them are computationally intensive, and I will show you that in our Monte Carlo simulations, they result in wider bounds than our delta method approach. And to illustrate these points, I would like to get back to the application, and I announced earlier. And in this application, we study possible effects of announcement of unconventional monetary policy that took place in 2010. In few words, what the unconventional monetary policy is. Recently, during the Great Recession, the interest rate in the US and a number of other developed countries was very close to zero, and that means that central banks, they could not longer stimulate economy by reducing interest rate. You cannot reduce interest rate any further below zero. So Federal Reserve came up with a number of unconventional monetary policy measures. One of them was so-called quantitative easing policy that involved large-scale purchases of long-term government bonds with money. And that policy was implemented in the first time in 2010, and in the past still. So now I would like to provide some bounds based on our method for effects of that policy. We can argue that we assume that that stimulating policy, that unconventional monetary policy, could have some positive effects on inflation, on CPI index, in consumer prices, but we also allow it for zero effects. At the same time, it could have or it could have not have some effects on industrial production, but if it had any, then effects have to be positive in the first period. At the same time, we assume that intervention in the long-term bonds market reduced rates on the long-term bonds. So it had negative impact, but it had no impact on federal funds rate, which is a short-term rate, because it already was at the zero level and couldn't be changed any further. And this type of restrictions fits into our setup perfectly, and we used data prior to the Great Recession, prior to 2007, and our practical goal is to use only data available prior to that announcement and try to and see if we can provide meaningful bounds for subsequent dynamics of the time series based only on those restrictions. And we can do so by estimating structural VR model and constructing our bounds. So I'll show you 4 diagrams. So this picture corresponds to dynamics, the true dynamics of a given time series, and these are consumer price index, industrial production, long-term rate, and this is federal funds rate. So the gray line corresponds to real dynamics, and the blue bounds corresponds to bounds provided by our method and imposed over the value at the moment of QE announcement. And you can see that, so the first observation is that the the true dynamics of all 4 time series fits very well within a 68% confidence set. So this is the first good signal. Next observation, the bounds based on Gleason methods, they are tighter, and you can see that they do not cover the true dynamic very well. Computational time for our procedure is just 0.15 seconds, less than a second. For standard Bayesian procedure, it takes 5 minutes. Not a big deal, but if you consider computational time for other methods that are robust to prior assumptions, computational time would be a major factor. So our procedure does much better than Giacomini and Kitagawa. So regarding the length, there is one more procedure based on frequency approach provided by Mucho, Friday, and Garcia. So it's based on the moment inequality approach. So we can compare bounds based on our delta method with that procedure, and our bounds are tighter in this example, uniformly over all horizons and all 4 variables. And final slide is the Monte Carlo coverage for our delta method confidence set based on estimated structural ER using American data. And you can see that if we construct confidence set based on 68% nominal size, then the coverage in finite samples is never below 68%. It's slightly larger, and it's larger because we have to deal with non-differentiable bounds, and I don't have time to go into details while we have to be conservative here, but this is a good thing. We can guarantee that we at least meet nominal size. So this is it. So our method is computationally efficient, and it doesn't require prior assumptions, and it's very easy to implement and compute. And actually, we provide a toolbox in MATLAB so that anyone can use it.
Any questions? So on the coverage, since your method is pretty quick, is there some sort of bootstrap you can do that would give better coverage?
Yes, you can. Improve coverage in some specific examples just by replacing delta method confidence set with bootstrap. Yeah. But the problem with that approach is that it only works if those upper and lower bounds on impulse response functions, if they are fully differentiable. So bootstrap only works under full differentiability. In general, this is not the case. There are certain values of reduced form parameters under which you lose differentiability. In that case, this faster bootstrap procedure would have coverage below 68%. And we actually show a proof in the paper that the bootstrap procedure you have in mind, it also has, under full differentiability, it has correct Bayesian predictability in addition to correct coverage. But that only works under full differentiability.
And there's not some variation like subsampling which you can...
no, subsampling in general wouldn't help. Wouldn't help.
Okay, any other questions? All right. Thanks again. Okay, the next speaker is Takuya from economics. Go down the bottom.
Oh, okay. So
so much for this opportunity. So I was not sure who is the audience, so let me introduce myself first. So my name is Takuya. So I got the PhD from Duke last year, and I've been here last year. So my research field is microeconometrics. So particularly I'm interested in the interaction between two problems in econometrics. One is data collection problem, the other is a structure problem, a structure model. So namely, like one of the examples for data collection problem is mismeasurement of variables. When you collect data set, you have a hard time to figure out survey respondents telling truth, or they are telling truth, or they're messing up something. So there's mismeasurement problem, measurement issues. The second problem in econometrics, in social science in general, we have a hard time to get experimental data. So data is coming from observational data. So there's huge endogeneity problem. So in this sense, I'm curious about two interactions between two fields: mismeasurement, measurement error, and endogeneity problem. So particularly my strength is the misclassification. So misclassification is a special case for measurement error, for binary variable, discrete variable. So which means maybe truth is 0, but the measurement is 1. But truth is 1, measurement is 0. So it's not like additive separable measurement error. It's a misclassification. So today I'm going to talk about my JOMAC paper last year. So this is a paper, I claim this is the first paper to apply instrumental variable to heterogeneous treatment effect when binary treatment is both mismeasured at the same time endogenous. So this is the interaction between two fields, endogeneity and measurement error. So my biggest question in this paper is what we can learn from data set about treatment effect when there's two problems. So answer is we cannot learn everything. So we cannot get point identification. So this is why I'm going to talk about partial identification as Bulat talk, today's talk. So my paper is instrumental variable approach. Do you know instrument variable? Okay, that's good. Then my approach is non-parametric. So I will not assume any parametric form in outcome equation or treatment assignment equation. So in this sense, robust for specification error. So this is, I think, new in the literature in measurement error. So my paper does not assume any assumption on measurement error itself. So the literature of measurement error assumes a lot of assumptions on measurement error, then figure out what we can learn. But my approach does not assume any structure of measurement error itself, more like getting information somewhere else. I will explain later. Then as a result, I get a bound or identification. So this is an overview, so it's theoretical result. So let me talk about some motivational examples. So I have two motivational examples. So this was my JOMAC field. So how many people who in this field has PhD? Good. So based on US census data set, there's one result saying around 70.7% who claim they have a doctoral degree does not have a doctoral degree in census data set. So it's census, so nothing special. So this is why measurement error in the data set is important. So let's say like, let's focus on some specific example, like return to college attendance is a typical topic in nearby context. So T star is the college attendance, whether you have been to college or not, they one variable. Y is wage. So there's endogeneity problem, which means U star unobservability affect T star and the U outcome variable at the same time. So this is why this is endogeneity, omitted variable bias. So what people do is using instrumental variable like Z. So Z only affects T star, does not affect Y directly. So one example for Z is like the grown up near college or not. So you have better access to college. So it's Z1 variable. So the twist of my JOMAC paper is T star is not directly observed. We can only observe measurement of T. So T here. So T, the self-reported college attendance, is not necessarily equal to T star, the true college attendance. So this is a measurement misclassification issues. So So since this is a general audience, let me talk about another example, more economics. So another example is impact of 401k pension plan on saving. So people talk about what if we attend to get the pension plan of 401k, it's a defined contribution. What is the effect on saving? So 401k participation increase saving or not? So there is an endogeneity problem. Right? Saving preference in people with the 401k eligibility. So some firm adopt 401k system, the others not. So we have some exogenous shock. So there are paper again. Some paper talk about in some data set, around 1/4 of the case has misidentified their pension type. So there is a measurement. So there's huge applications, interaction between measurement error and endogeneity, even in simple case. So this is my journal paper. And from here on, I'm going to talk about more theoretical stuff. So if you screw somewhere, don't worry. So my journal paper is focusing on some flexible measurement error or non-classical measurement error. So as I said, the true treatment variable t star is binary. So error, measurement error in between t and t star is non-classical, which means the difference between measurement and truth is dependent from t star. So the reason is obvious. So t minus t star can take -1 or 0 when t star equal to 1. The reason why is when t star equal to 1, t can take 0 or 1. So t 1 0 minus 1 is -1 or 0. When t star equal to 0, t minus t star is 0 or 1 because 1 0 minus 0 is 0 1. So measurement error itself actually has support itself is dependent on value of t star. So we cannot assume independence. So most of the paper in measurement literature assume independence, but I cannot because I'm not going to talk about binary treatment variable. The second stuff I'm allowing for in my journal paper, my previous journal paper is, I'm not assuming endogeneity of measurement error. I'm not assuming exogeneity of measurement error. So U star is arms of heterogeneity, which affect T star and Y at the same time. It's the source for endogeneity. Actually, this U star also affects T itself. So the idea is, if you are smart, you are more likely to go college, you are more likely to get higher wage, you have better precision in the data. You have better recall, or you are used to answering exams. So answering exam and answering dataset survey is kind of similar. So U star ability is also related to T, the F. So this is called endogenous measurement error. So I'm allowing for it. So there's a bunch of paper in endogeneity literature and mismeasurement literature. The interaction is kind of few. So I have several papers, but time is limited, so I will skip this. The point is, if you care about the binary, mismeasured, and endogenous treatment, my paper is the first one. So contribution of this paper is a few points. I will not talk about inference today. So identification. So I can identify in some way the local average treatment effect. So local average treatment effect, I'm going to explain, has two assumptions. One is exclusion restriction of instrument. The other is monotonicity. The monotonicity means instrument increase treatment variable in deterministic way. So I'm going to assume these data assumptions as literature do. Then I'm going to allow for arbitrary measurement error. So my result is partial identification. And notably, I can identify two objects. One is sign. So I can identify sign of local average treatment effect. 0, negative, positive. That's great. We can get sign of this. Then in bounds, I can get lower bounds and upper bound on local average treatment effect. So even though I could not get point, I can get a bound, which has either positive side, negative side, or 0 side. So my result is sharp, which means exhausting all information from data set and models. So that is have to understand. So let me talk about model, then talk about result. So my model has 3 equations. So let me explain one by one. So first one is, what is a relationship between T star and T? So this is a measurement equation. So when T star equal to 1, T1 is observed. When T star is 0, T0 is observed. So this is a relationship between T star to T. The second equation is a relationship between T star and Y. So it's the outcome equation. What's the relationship between T star and Y? This is what we want to know. The last one is the relationship between Z instrument variable and T star. So it's hard to get, so there's a graph, so let me explain. The first one is talk about what the relationship between T star to T. How truth affect measurement. So it's measurement equation. The second one is how T star affect Y. So how true treatment variable affect outcome variable. So it's outcome equation. The last one is how instrumental variable affect true treatment variable. It's called instrumental treatment assignment equation. How instrument affect true treatment variable. So assumption is following. So instrumental variable is exogenous, so which is independent from the other terms. The second one is monotonistic. So when we increase the instrumental variable Z0 to Z1, T star is going to be strictly increased with positive probability and never decrease. So it's weakly increase always. And local average treatment effect in this framework is, so let me explain. Local is we are conditional some population, subpopulation. So this subpopulation called compliance. So the meaning is if you move instrument from Z0 to Z1 who are affected by instrument such that they change to treatment. So it's not equal. And average is expectation factor. And treatment effect is Y1 minus Y0. That's treatment effect. So if you remember one slide from my talk, please remember this slide. So basically I spent 5 years to make this slide. So identification, my identification result is sign and bound. So let me categorize 3 cases. The first case is if I can identify sign of local average treatment effect as positive. This is 0 case and this negative case. So when we identify the local average treatment effect is 0, so this is can be identified as by intention to treat effect is 0. So when intent to treat effect is 0, so I will define data. Local average treatment effect is 0. When intention to treat effect is positive, this is identified set of local average treatment effect. So there are several points. So this is positive in the region. And there's lower bound and upper bound. So first of all, ITT is the regression of outcome variable on instrumental variable. So idea is, since your treatment variable is endogenous and mismeasured, so it's kind of like nearly garbage. You want to throw it away. So just regress outcome variable on instrument variable. It's intention to treat it. So this is lower bound for local average treatment effect. The second one is word estimate. So word estimate is the limit, the probability limit of 2SS. So which means if you ignore measurement error, just take into account endogenous issues. So this is what people do. You actually overestimate local average treatment. And second point is your 2SS that is not only overestimated, but it's not sharp either. So you could do better job to get upper bound. But you are giving up to talk about that upper bound. So in this sense, you could use 2SS and still claim upper one, but it is not sharp. And negative case is symmetric to positive case. So this is my geometry paper. The contribution is actually here, and this is the figures. Does it make sense so far? So how many minutes do I have? 10. You have two choices. I'm going to talk about theory or empirical applications. Probably empirical applications better. Yes.
Why don't you know? Just ask people.
Okay.
So ask an empirical illustration. Who would like that?
Who like that?
If that's
Empirical application. Who like theory?
yeah. So the empirical has.
We can talk later.
Yeah.
So my empirical application is I'm going to figure out the effect of the 401k participation on financial savings. So I'm going to use my method. So the complication is twofold. One is 401k participation itself is endogenous in the outcome equation of saving. Because if you care about saving a lot, you are going to think about 401k seriously. So you are more likely to participate, and you are going to save more. So this is endogenous. The second one is the self-report 401k participation can be misclassified. So there's one paper talking about one-fourth misclassification. So I'm going to use a survey of income and program and participation, SIP data of 1991. So this has been used by several people, and so this data itself is panel that I'm going to use as cross sections. Yes.
So how does Gustman know?
Oh.
Somebody
Yes.
incorrectly stated in the survey.
I was curious about the direction of this
Yes.
classification and scale.
Yes. It's a very good question. So his paper is not using SIP dataset. So his dataset is using University of Michigan's Health and Retirement Survey. So Health and Retirement Survey has administrative part. So they can compare self-report and administrative part of their pension plan. So they can match like, employee and employer answers to the pension plan. So they can match. In this way, they can clarify what is the difference between employee and employer answers to the same question. So this is how. And second question is false negative and false positive. So I need to go back to last month's paper to be precise. But I think false negative is large, which means even if somebody has defined benefits, defined contribution, they do not know they're actually contributing. So as a result, they say, I don't have any DC plan. I don't have any 401k plan. So in this sense, false negative is larger in my memory. But I need to double check to be precise. So SIP dataset itself is panel, but I'm using as a cross-sectional dataset. So this is the household survey in large scale from US civilian and non-institutionalized population. So how I'm using is following. So just I'm showing key variables. So Y is net financial assets, and T is self-reported participation in 401k. And Z is eligibility for 401k. The meaning is the company has a system for 401k or not. So there are several complex variables: the family income, age, marital status, and the family size. And summary statistics for key variable is following. So Y is like $19,000. How many people in 401k participation? It's like 27%. Oh, so this is 1991. It's much lower than usual. In the current, it's much higher. And 401k eligibility is like 40%. And my final sample size is 9,000-ish. So the reason why is I sample set similar way to previous research. Basically, household is at least one person is employed, because otherwise we cannot talk about pension type plan. And there's no income from self-employment, because self-employment makes more complications. And the first family income is not too low, too high. So next slide is result. So if you apply QSAS, the effect of 401k participation on saving is $60,000. It's huge. But it's a result in the previous literature. The confidence interval is like $6,000 to $27,000. It's huge, but nothing wrong with it. So that's fine. The intent to treat effect, which means the regression of y on z. There's some control variables, but this is the case. It's going to be $10,000. The confidence interval is like this way. So as I said, intent to treat effect is lower bound, and word estimate is upper bound. This is sharp, it's not sharp. It's rough upper bound. So my confidence interval is following. So I show 90% and 95%. So there's tuning parameters, but it's relatively stable across tuning parameters. So let me focus on the BPS case. So for lower bound for confidence interval, I have $4,000 as an effect of 401k participation on saving. As upper bound is $28,000. So it's more or less similar to the result of local average treatment. Even though it's not clear there is a misclassification or not, at least my result is robust to misclassification. So in this sense, I'm like supporting previous research result. Even if we are talking about the worst sense check in terms of measurement error, you can still get quantitatively same result. So let me wrap up. So my paper is the first paper to apply instrumental variable, the heterogeneous treatment effect of binary variable, which has two problems, measurement error and endogeneity. So I characterize the sharp identify set. The feature of this very arbitrary measurement error, so non-classical measurement error, endogeneity in the measurement error, actually no assumption on the measurement accuracy. Then in the proof I'm using some new implications from exclusion restrictions. The integralism is the 401k effect on saving. And what I show is the previous result is pretty robust. It turns out to be robust against this classification. So I cut off proof, but this is what I have done for German paper.
So you have a couple more minutes if
Yes.
you wanted to talk about the theory or
Oh,
your choice.
that's a tough call. So I cannot talk about this theory because theory take 2 minutes of preparation.
Okay.
So let me talk about maybe for PhD students. So I think even though this field is narrow, measurement error plus endogeneity, there's still like source we can talk about. For example, I have a journal paper, this one about average treatment effect, and I wrote paper about quantile treatment effect. So both are very important. And there are many papers talk about endogeneity, say simultaneous equation models. It's a typical case of actually Bulat is one example. It's simultaneous model. So in this sense, I feel there's still source we can produce papers or get attention from applied people to talk about both data collection issues and endogeneity. So if you are interested, let me know. Safe advice might be here.
Okay, thank you.
Yes. So,
Yes.
Takuya, so those bounds
Yes.
where if the effect is positive, then the load estimator is too high, and if the effect is negative, the load estimator is too low.
Yes.
What happens for inference when you're close to zero? So that any
Yes.
draw, you might switch signs.
That's fair problem. So this is identification. So in the inference, it's possible to have both sides. So it's not clear. So if you're completely right. So this is same as like usual instrument by regression. It's not guaranteed you can have both sides as one side. You can get both sides because of sampling error. So what I'm claiming is if your confidence interval covers positive and negative, this is sampling error problem. It's not identification problem. So this is the most I can say. I know I'm not answering your question directly. This is the best I can answer.
Any other questions? Okay. I've got a couple. So one is, if there was no classification problem,
Yes.
would you basically get the WOLD results and get similar confidence interval width?
That's a good question. So it's kind of fundamental problem in the measurement literature. So there are two cases. We know there's no measurement error. Second case is we do not know whether there's measurement error or not, but it turns out there's no measurement error. In the first case, it's always use what estimate and construct confidence interval based on what. The second case, we do not know exactly there's a measurement error or not. It turns out there's no measurement error. You should use my method because we don't know before.
I was just surprised. I mean, normally when you have the bound stuff and so on, you get substantially wider confidence intervals.
Right.
But it turns out in your application, you didn't.
So I will not say it's happening everywhere.
Yeah.
I choose applications for sure.
Yeah.
So that, yes.
Well, I just wonder whether that was a signal that there wasn't a classification error problem.
But there is a reason. So if you look at T and Z, so Z is 40%, T is 27%. So in this sense, the instrument is pretty strong.
Yeah.
So even though there's measurement error in T,
Yeah.
I'm assuming there's no measurement error in Z. So you can back up a lot of stuff from just Z. So this is the critical reason.
All right. Thank you very much. PowerPoint. Yeah. Control L. Oh, no, yeah, no, he's got PowerPoint.
That's mine.
Okay, so final speaker of this session is Prasada Naik, who's been in the Graduate School of Management for
20 years.
approximately the same time at the time I've been here. Take it away.
All right. So, well, thank you, Colin, for inviting me. I did not know that you already had two such events in the past, but I saw your mail which said third annual statistical methodology in the social sciences. So, I don't know the genesis, but maybe at lunch we might chat about it. All right, anyway, thank you. I suppose many of you are actually doctoral students, and I didn't really think about that because we have no PhD program in the Graduate School of Management. So when I talk, I always talk to faculty. And so I said, oh my God, I'm going to lose everybody because I'm going to keep it at a high level. And so it's just softer ideas, and then there is hard technique, okay? So if you don't follow, it's perfectly fine. It is not meant to be followed for some reason. But if you follow a little bit or you think you're following, then come and talk to me and I'll explain to you that you don't really follow. Okay? All right, so with that, let's go with this. So the paper is already published, okay, and that's what you told me that I could send. Normally, I do not present things which is already published because you could go and read it. So there is no reason for me to come and tell you the story. But since you allowed me that, I said, well, that will make me make fewer slides because the talk was already presented elsewhere. And so it was low-cost laziness by which I chose this paper. So what we do in this paper is we derive what I call robust filter, which is a general approach to estimate dynamic models, just as general as the Kalman filter. And we show that the Kalman filter is actually not robust. And in fact, we show that it is the least robust. So any of this, so you can think of what the filter I've done. There's a parameter, one parameter called gamma. And you can index all such gammas from very low to very high. At the extreme value, when gamma takes infinity, there is the Kalman filter sitting there. So if you put any finite gamma, you will be more robust than the Kalman filter. Okay? And the Kalman filter is nested. You guys know what Kalman filter? That's what I meant. I'm going to start saying things which you might wonder who the hell is carbon filter.
Most will not.
Most will
Yeah,
not.
I don't.
Okay, so I have to back up here. So carbon filter is an approach to estimate any dynamic model. Okay, so you can have a differential equation, you could have a difference equation, you could have equation with measurement error in y, you can have measurement error in x. If the model is linear, then it can always be recast. So ARIMA models, for example. All ARIMA models are special cases. Okay? And there's only one algorithm called the carbon filter, which will give you maximum likelihood estimates or EM estimates or Bayesian estimates. If you did ARIMA models, then for AR there is one way to estimate. If it is MA, then there is another way to estimate. If there is an integrated, then there is yet another way to estimate. So there are as many methods to estimate as there are models. And so it brings a unification of any dynamic system. And it's multivariate, it has all good properties. Your cell phone, by the way, just to give you a tidbit, has a little GPS. You guys use that? Or your car? That's a carbon filter. Okay? So the carbon filter gives you your current location and velocity every single instant through the satellite. So if you make a wrong turn and it says recalculating, you guys hear that? I hear it all the time because I can't drive well. That recalculation is that filter is trying to predict what your next location is, but observation has departed far away from what the filter is thinking you should be at. Okay, and that's the departure is what, so the innovation is very high, or the departure. Anyway, so it is used in many places, typically in time series models. So we derive something called robust filter, which is robustification of the carbon filter, and then we apply that to the blood data from Canadian setup. And the reason we chose that application is because we wanted to have fun in the first place, but then we have to actually publish. And then we say, well, what application can we bring where I can make the claim credibly that robustness was required in the first place? Okay, so normal data that I deal with is dependent variable sales. Sales could be number of units sold of, let's say, Cadbury's chocolate or detergent. And I say, well, my demand should be forecasted with some robustness. And if, let's say, chocolate demand was not forecasted with robustness, or GDP for that matter, nothing really goes down. Okay? You just move on, saying, okay, fine, it's not robust. Okay? Same thing with standard errors around the hi-hat. But if it is blood, then it's a very different question. So if they want certain number of bottles in a hospital, and if you send less, people will die. And if you send more, then blood is perishable. You collected people's blood, and then it will go waste. And so they really need a proper forecast of how much range you really need in that standard error as well as the mean. Okay? So that application is very important. And I'm going to talk about, so in the paper there is another part, that one is just the forecast, and the other is what I call normative, meaning you prescribe the Canadian Blood Services that how much advertising should you do, phone call and radio. That's what they stimulate demand for people to come and give blood. And so if you do a lot of phone calls and a lot of radio advertising, many people would come and you will have lots of bottles. And if you don't do it right, then there will be fewer and then people will die. And that cost is asymmetric, right? I mean, if you have excess, there's wastage, but wastage is cost, but not as important a cost as shortage, when people would die. And so the cost function on whether you owe on excess or not is very asymmetric. And so we want to discover what is the right level of advertising on radio and the phone call that you should do to manage this asymmetric cost of inventory. Okay? So that's the control problem is what we call. I'm not going to get into that because it's only 25 minutes talk, but it's there in the paper, so you can go and read. And by the way, the paper is There's a link there. So if you click it, you will need UC Davis access to get into the journal store. But you should have that, right? I mean, most people have.
It's marketing science, right?
That is marketing
So
science.
just Google your name, marketing science.
Yeah, you know, it will come up, but it doesn't allow you to see the whole paper. It just gives you the abstract. So you will need the UC Davis VPN. You can just send me an email and I can give you a copy. Okay. All right, so here is the empirical example. And so we have data from, oh, I didn't mention, this paper is with my colleague Olivier Rubel. He is now an associate professor in the last 2-3 years. And he was in Canada. And when he joined us, we started this project. It took us 6-7 years to come to this state. But that's how it is Canadian data that we got into. He primarily collected the data set. And we have data on all sales in Canada except Quebec, which is a French-speaking country, province, and they have different policies on the collection of the data. Data meaning, sorry, blood. Okay, but rest of English-speaking has another policy that there is only one monopoly called Canadian Blood Services who can collect the data, and they give it free to every single hospital. And it is funded through government funding. Okay, so there is no competition and there is no price, and that's another thing we needed, that we wanted to specify a demand model in which there is no other things in it, no price and distribution channel, and so clean data, no channel, no competition, no price, only thing that works is advertising. And that was like a perfect heaven for me. I said, this is the data I want to work on. Alright, so the dependent variable is number of blood collected per week. As in your case, there is measurement error. V is normal, it's not 0, 1 for like you. And a square root h would be the standard deviation of the noise of the VT. So VT is 0, 1, normal with mean 0 and variance 1. And the standard deviation, you can think of it as h. And not standard deviation, variance. Same here, omega t is standard normal, you can think of it as standard normal. And Q is the variance. And then this is your AR1 process. So this is your mean VT, which is the amount of blood collected, pints of blood. And this is last period's blood, so it's an AR1 model. And U1 is radio advertising. U2 is the phone calls. So that's an effort. And you can put more effort, that will get you more blood. Right? So you make more phone calls, more people will come. But if you keep making more and more phone calls, it's not going to grow linearly. So there is this diminishing returns. And so that's why there is square root. Simple model. And this would fit a state space model or the Kalman filter very nicely. So y would be y, alpha would be my b, z would be 1, but z could be a matrix and y could be a vector and alpha would be a vector, and so it's very general. But the example is scalar. Okay? And then this is b, and then t would be my phi. You guys mapping it, right? And then this drift would be all that beta square root u1 plus beta 2 square root u2. That's the drift. And then there's omega, which is noise. And Vt here is distributed with normal 0 matrix H. Omega t is normal 0 matrix Q. So mine is a scalar example, but the filter state space model. And this is a standard state space model. Observation equation, and then this is a transition equation. Alphas are usually not observed, that's why it's called transition equation. And y is what you observe with error. So in your GPS example, you only observe your location. Okay, so the satellite only knows where you are, latitude and longitude, and it knows that your z velocity is 0, meaning you are not high, going high. So it doesn't report any altitude. So you only have 2 dimensions, but your alpha is much more. It knows your velocity in the x coordinate, it knows your velocity in the y coordinate, the two planes, as well as the location in these two. And if you're going up the mountain, then it will also know the altitude and the altitude, and the location of the altitude. And so this could be a 6-dimensional vector, x, y, z, and then the velocities would be x dot, y dot, z dot. Okay? So you only observe 2-dimensional data on where you are, but depending on how fast you move, it will infer what your velocity is. Okay? And that's how, if you are stuck in traffic, it knows that this estimated arrival time needs to be changed, because it knows you're stopped, your velocity is 0. Okay? All right, but it has been used in many other applications. So it's a very broad class of models, time-varying parameters. So you can think of this as your regression. Okay, so just imagine this notation, that this is y, this is x, this is your beta, this is your error. So this is y equal to x beta plus error, standard regression. But instead of getting you one data, you can say my beta is changing from period to period. Okay, so you can think of a slope which is also going up and down constantly. And then you say, well, that's my slope which is changing over time. And slope itself could be a function of other variables, and that would be a hierarchical linear model. So it has many other, so var is a special case. You can think of var and put v equal to 0, your var will become a special case. ARIMA, dynamic factor models, many models are special cases of that. Alright, with that, I want to just point out the main thing, that when you estimate these models, you will either maximize the likelihood function or do the Bayesian and get the posterior moments via the Kalman filter. All of that generally assumes normality. Okay? And that gives you very good properties, and nothing wrong with assuming normality. But I'm just mentioning because I'm going to now come to a different way of looking at the problem. Also, once you estimate the model, you want standard errors, you get standard errors from your likelihood theory. And then there is something called a sandwich estimator, which is by Hal White, and blockbuster paper. And you can have a more robust version of that standard error. So there exists robustification of the standard error. But the main drawback of such a procedure is that the estimate remains the same. It is at the estimated MLE that you are going to evaluate the gradient matrix and the Hessian matrix to get the sandwich estimate. But the parameter itself do not change just because you are computing a standard error. So the likelihood estimate theta hat is the same. The standard errors will expand or contract a little bit from MLE. But if your theta hat is the same, then any function of theta hat will be the same, whether you use sandwich estimator or you don't use. And firms will use some function of theta hat, meaning how much should I spend on advertising. If you tell me that elasticity is 0.2, it's not the elasticity I care about. I want to map that elasticity to actual dollars in budget. And that function is going to use that elasticity estimate, and that will be the same whether you use standard Hal-White's result or not. Okay? So the robustification of the term is only going to change the range of my spending, but not the mean of my spending. So we came up with this idea where we said we will now do something called robust filter. So I want to now come back a little more softer. Okay? So it's nothing per se about filter right now. So you can think of a linear regression model. Y is your dependent variable, X is your regressors, alpha is your betas, and omega is your noise. And if you are frequentist, then only omega is the noise, alpha is fixed. And if you are Bayesian, then both alpha and W are fixed. Random variables. You guys tracking me, right? Alright, so now what does really most of frequentist guys do? OLS, everybody, okay, maximum likelihood. That you will set up some loss function. Loss function is a metric between how far is your model from the data. It could be OLS and it could be y minus x beta whole square. It could be lasso, and you'll say, well, I'm going to take the quantile regression, and I'm going to take absolute value. Or you'll say, well, I'm going to form a likelihood function, take the density, multiply all the conditional densities, and then treat that density as a function of parameters rather than the densities. And that would be my likelihood function. But it is just a measure of distance between the model and the data. Okay? And I'm going to call that as a loss function. Some metric that I'm going to minimize to come up with some value saying that this is a good estimator. Alpha is fixed in ML, and so you only take the expectation of that over whatever is random, so that is omega, and then you minimize that loss function. If it's likelihood, you maximize it with this quadratic square error loss, as in Gauss, then you would minimize. But they are both the same, exchangeable things, minimize, maximize. And so that's what's going to get you at alpha hat. So alpha hat is an output of this program. Okay? Bayesians will say, well, we don't like maximization. I'm going to do all these CMC, as long as the world spins. And then it's going to give you some answer. That answer is really taking an expectation of the posterior of the random samples of alpha. But it's eventually the same idea that you will need a function to maximize, and then you're going to evaluate expectation over the random variable, and then another expectation over random variable, which is replaced by the minimization operator in the likelihood table. Okay, so both approaches are very similar. And when you say standard errors, it is just the level set of the two. So really, there is not much difference between estimation in ML or Bayesian. Both will require distributional assumptions. Bayesian will require stronger distributional assumption because it will require not only for omega but also for alpha. Okay? But distributional assumption you must have to make. Anything. So you can call it gamma. In your case with measurement error, you will think of it as a binomial. But you will need some distributional assumption. So now I'm going to suggest an idea which will lead to the robust filter, that you don't really need any distributional assumption. Okay? Any meaning absolutely any. So distribution may not exist. Okay? So what you could think of, let's say you have this model y is equal to x alpha plus error. Okay? You think of it as a game. Game as in a differential, not differential, as your economic game, like a game theory game. Okay? And think of it as a tug of war. And the other side of that tug of war is nature. And your job is to find out the value of alpha. And you say, I'm going to find my alpha by taking a quadratic function, y minus x alpha, square it up, add it up, and minimize, and that's my alpha. The other side, all these years along, when you didn't think about this robust idea that I'm going to explain to you, there was a random error coming from somewhere. You never thought why it came. Your instructors from your 12th grade said that there is an error in the regression. And you accepted the fact, of course, plus epsilon. It has mean zero, normal, shape, density, PDF, CDF, moments, NGF. All those things you learn. But never question why this alpha error came up in the first place. Okay? Usually it doesn't come up because of economic theory. Economic theory comes on a deterministic basis. Same with physics. And then statistician comes and throws an alpha, the error term. And you say, okay, fine, I'm going to find my alpha hat, given that there is some random error. I consider that as a passive introduction of error to perturb your model a bit. But you can think of that passive view as more active. So think that there is somebody actually throwing this error at you. And he or she is throwing that error with some strategic intent. Okay? And you, so nature is throwing an error at you to degrade your signal. And whatever y I get is my signal, x alpha, plus the noise I got from someone. And my job is to infer what is the best alpha given that you are going to pull this tug of war. So you are trying to impede me or defeat me and perturb and make it contaminate my life because of this little bit of struggle that you posed upon me. I'm going to anticipate that. Then the nature is also going to anticipate that you are going to anticipate. And then they are going to get into this game, which is why it's called tug of war, because it is a zero-sum game. And they will reach an equilibrium where this game can get played. Okay? Of course, nature can throw a very huge bad luck at you, and everything goes down, and then there is no solution. Oh, 5 minutes, wow. And so this is the main idea of a robust filter. And so once you get that, I'll ignore this. Okay, let me not ignore this. So the key idea is you solve for the equilibrium of the random draw that nature will throw at you without making any distributional assumption. It is a deterministic sequence of omega hat that you will get. And under that deterministic sequence of omega hat, you say, what is my best alpha hat? And it is your best response to nature's best play. And both of you are stuck in this equilibrium for the game, and your goal is, of course, the alpha hat. And you substitute and you get some filter, and it is just like Kalman filter. There is a proposition 2 that will prove what the filter recursions look like. Very similar, except that there is a parameter gamma on how robust I'm going to be against nature's impedance, which is thrown at me. Okay? All right, so there's a Kalman filter, and we go ahead and we do robust filter. We get robust parameter estimates and robust inference. If I do White's correction, I get robust, non-robust estimates, meaning the same as maximum likelihood, but robust inferences. And I can do the same idea for my robust filter as well. And then I get a combined approach. So we did this empirical example with this blood marketing with 5 provinces in Canada. There's radio and phone calls. Radio is GRPs per week, which is a mass advertising. Phone calls, you dial the phone and talk to people, which is very effective. But of course, you can only do so much. And that's descriptive stats. And across all 4 conditions, we estimated the parameters. And of course, these estimates are exactly the same because this is just the same maximum likelihood, but the standard errors are different. And if you go down, then the estimates are also different, and so are standard errors. Okay? And if you do combine, then of course, these estimates are the same, but the standard errors would be different. We go and solve for a control problem and all that, there are a lot of other results. But for the filter and the Kalman filter, so this is what we propose, this is what exists. In sample, Kalman filter wins. Okay? Because we allow a certain robustification, and that is not the optimal filter. The optimal filter is the Kalman filter, where you do not impose any such idea of robustification. And therefore, in sample, mean square error, mean absolute percentage error, MAP, and we also had a 4th one, which was also the same results. Kalman filter in sample beats robust filter. Out of sample forecast. Okay, so this is holdout sample. So non-training data set, test data set, as Colin was saying. There we uniformly beat on every single metric in every single state in holdout sample. And so robustification has value not in getting sharp standard errors. In fact, the standard errors will be wider. Parameters will be slightly more biased. And in sample, you are actually performed poorly. But if you are going to forecast in the future, you will be protected against outliers and wrong things and fluctuations much better than the Kalman filter. And much better meaning anywhere between maybe 10 to 30%. In the applications of blood, that's saving a life here and there. Application of demand for chocolates, probably not. And so use Kalman filter for normal things. And something which is really serious, think about a robust filter. Thank you very much.
Any questions?
Yes.
Can you use the GPS case to really show us the pro of your filter, robust filter? So, for example, if we replace the common filter in GPS with yours, what
No, not a good
advantage?
idea. But if you are putting man on the moon, which they was the first application of the common filter, and the robust didn't exist at that time, they would prefer that. Because you do not want to end up on Jupiter. You say, oops.
Because it's hard for me to visualize your minimum maximum principle in the sense that, it's still you are assuming a very extreme case of the distribution of the error time.
No, so okay, very good point. So let me point this out. So think about that omega, the noise, could have been any distribution. It could be normal, it could be gamma, it could be uniform. So some noise. I'm saying use none. So if I'm going to use none, what am I going to use for noise? I'm going to use the worst possible noise that could occur under all possible distribution. Some sort of an ordinal statistic across all densities. And so I'm going to get the worst case scenario for my noise, and then say, under the worst case game that the God could play with me, what is my best response? When you're using OLS, that's what I meant by active versus passive. Passive, you're going to say, oh, your density is going from 0 minus 3 plus 3 is the only shock that I'm going to get. What's the big deal? Assuming it's normal and all that. But the game where nature can throw at me, he says, oh, he's getting it so nice, let me give him 7. I have to predict that in the game theoretic sense. And then plan my strategy that if you were to give me 7, what would be my alpha B? If you were to get me 9, what would be my alpha B? So for all possible outcomes, I'm going to compute what my strategy is and then decide in the worst case what will happen. The worst case is obtained by maximizing. So if you see that argument, we arg min max. It's called mini-max principle. So I'm going to take the maximum the value of the error, meaning the maximum disturbance possible, and then minimize my loss function. So I'm going to solve two simultaneous optimization for programs, where I'm going to say that in the worst case scenario, what is my best estimate? So best estimates for the largest errors.
So, forgive me if I didn't follow the intuition. If you're calculating the alpha based on a worst scenario, intuitively the interval you got would be the most conservative one, which
Yes.
that probably would explain why the outsample performance is better for your case, because
Yes.
you're trying to calculate what's
The worst
best
case
for the
scenario.
worst scenario.
So for normal applications, don't use robust filter.
Okay.
But if it is worst case, so now you got to think what King John Yoon would do. Military is thinking a robust response. In the worst case, what will be your response? In the normal case, what will be your response? In the best case, what will be your response? Then they are going to optimize over this. So they are going to do min-max to say what would go wrong in the worst possible scenario and what would be my best response. If the best occurs, it's not too bad. Okay, and so it is very conservative, as you point out. Yes, that's why in sample the performance is not good, because it's very conservative. Okay.
All right. Okay, well, thank you very much.
Thank you very much.